So today we're gonna be talking about Newton's second law and go and see all of the ways you could represent Newton's second law. There are many variations that have been added with when new mathematics has been found, right? So the most simple form is obviously F equals ma. So m denotes the mass, a denotes the acceleration, and F determines the force. So practice would say, like, if we had a car that weighs 1 kilogram and it's moving at 5 meters per second squared, well, what would the force have been applied to make it move? It would just be, well, it would be 5 newtons, right? Well, because we don't have to really convert because they're all in SI units. And that is the most simple part of Newton's second law. And we could also, well, I should write this again. We could also write A is equal to the second derivative of R with respect to time. That's a terrible T. And also, and this would just be equal to R double dots. Because of how much time derivatives are being used in classical mechanics, it is much easier to just write them as double dot, triple dot, and all that. So we could just rewrite F is equal to mr double dot. But this will apply to any function r of t. So let's say r of t equals sine of t. So if you want F as a function of time, it would just be equal to mr double dot. So r dot here, if you know the derivative of sine, this would just be cosine of t.
Oh.
And r double dot of t is going to just be equal to negative sine of t. So meaning that this equation, f of t, is equal to mass negative m sine of t. And you can see how this is kind of useful and how basic calculus can be applied to physics. But however, this doesn't take into account a mass that isn't constant. So, and if we want to do that, we have to recreate another definition for Newton's second law, which in this case is just the time derivative of rho, where rho is the momentum with respect to time is equal to the force. And the reason why this takes into account a mass that changes is because we know that from your definition of a momentum, this would just be m times r dot, where r dot in this case is the velocity, and taking the time derivative of that is equal to f. And meaning this, if you learn the product rule, this would just be m dot r dot, and plus mr double dot, because the product rule says that if you have the derivative of f of x times g of x, derivative with respect to x is equal to f prime of x g of x plus g prime of x f of x. And in this case, f of x is m and g of x is r, but this time we're taking the derivative with respect to time. And you can see that, well, f, right, is equal to mr double dot plus m dot r dot. And you can see how our first equation was f equals mr double dot, right? So this takes into account the changing mass, as you can see. So the time derivative of momentum is a more accurate way of saying for any given system that if you wanted to find the force. And you can see, and most of the times m dot r dot is equal to 0 because m dot equals 0, and the mass usually is constant. We can also write the force. So if you've learned some multivariable calculus, well, the integral of f vector dot to the dr vector is equal to the work. And because this dot product signifies that f and dr makes it so that f dot to the dr is a scalar. And we know that from the kinetic energy theorem that W is equal to negative delta T. And not negative delta T, W is equal to normal delta T. And delta T is equal to negative U. Meaning overall that, like, W is equal to negative U. I'm sorry, negative delta U. meaning that w is equal to negative u. So we have so if you wanted to find the potential alone, this would just be u equal to negative integral of f dot of di. And if you wanted to invert this integral, well, first we have to multiply negative 1 to both sides, so we just get f is equal to this. And if we wanted to only have one dimension, we could just make this equal to f dx. And well, you could just f dx. And well, this would just be our potential energy, is negative u. Well, in this case, you would only have to take the partial derivative in respect to x is equal to the force in one dimension. But if we wanted to still do the dotted dr in say 3 dimensions, well, f is equal to the negative gradient of the potential. We could also, so let's say we have our u of x, y, and z is equal to z squared y squared plus xy sine z plus y. So what exactly would the gradient be? Well, we know that the gradient operator is defined as the partial derivative with respect to x times I hat plus the partial derivative with respect to y and j hat plus k hat times the partial derivative with respect to z. So meaning that if you wanted to write the gradient, and also I should mention that this applies to only scalar functions. Well, del of u is equal to, well, what's the partial derivative with respect to x is going to be, in this case, the x component is I hat sine y sine of z plus j hat times, well, if you take the partial derivative with respect to y, is 2yz squared plus x sine of z plus 1. And finally, for the z component, this would be 2zy plus xy cosine of z, and times k hat. So this, and if you wanted to find the force, well, you just take the negative gradient. So just the negative gradient of u is equal to f, which is equal to I hat y sine of z plus j hat times 2yz squared plus x sine of z plus 1, and well, plus 2zy plus xy cosine of z times k hat. So yeah, this is kind of the application of, say, taking the gradient of the potential so that we can get a force. We could also, in fact, combine our definitions in terms of the momentum and the potential. Since for the sake of how easy it can be, we're gonna just say this as the time derivative of momentum is equal to negative partial derivative of u respect to x. So let's say we have a momentum of t is equal to, well, t squared plus 2at plus a squared. So just a simple second rank polynomial, and let's say we have u of x and t is equal to xt squared plus t x squared plus sine x. So if you want, so let's say let's take the time derivative of momentum. So taking the time derivative prime of t would just be, well, 2t plus 2a, and that's it, because a is considered a constant and rho doesn't depend on a. And u, and the partial derivative of u respect to x, well, this this would just be t squared plus 2xt plus cosine x. So if we wanted to equate the two, we would just get 2t plus 2a is equal to negative t squared minus 2xt minus cosine x. And as you can see, and you could simplify this if you want, but I don't. I think it's you can do that on your own and see what you could do. So that's kind of it for like how you can write Newton's second law, I believe. And it's basically been reformulated again and again. Basically the main point of classical mechanics is to try and describe the position of any given system or any particle at a certain point. And you see, we can have like let's say we have a ball falling, right? And the force on it would just be negative mg, right? Mg is positive. And we can write it in terms of Newton's second law. So if we were to have mx double dot is equal to negative mg, so meaning that x double dot is equal to negative g. So while integrating both sides, I should write like this: dt is equal to, that's terrible notation, integral with respect to t twice, and then you just get x of t is equal to negative gt squared over 2 plus some constant c, t plus d. And where c would just be the initial velocity and d is the initial position. So you see, Newton's second law is very important in that it creates you a differential equation for you to solve so that you can find the position of a particle at any given time t. So I hope you enjoyed that. I think it's pretty interesting and I hope you guys did too. So thanks for watching and I'll see you later.